5 years ago, if you searched anything about fasting, you would hear the same advice everywhere. Just do 16.8. Fast for 16 hours, eat for 8 hours, and your body will magically burn fat, repair itself, and reset your metabolism. Millions of people tried it. Some lost weight, some felt incredible. But something strange also started happening. A lot of people followed 16.8 perfectly, and nothing happened. The fat stayed, energy dropped, brain fog increased, hunger got worse, and researchers began asking a serious question: what if the way we've been teaching fasting is already outdated? In the last 5 years, the science of fasting has changed more than in the previous 20. New studies on metabolism, circadian biology, hormones, and cellular repair are showing that fasting isn't just about how long you stop eating. It's about when you stop eating, how your body responds to stress, how your blood sugar behaves, and how your cells switch between fuel systems. In other words, the simple 16-8 rule that once dominated the internet may not be the most effective method anymore. Imagine two people both fasting for 16 hours. One loses weight easily and feels energized. The other feels tired, irritable, and constantly hungry. On paper, they are doing the same fasting protocol, but inside their bodies, completely different processes are happening. Hormones like insulin, cortisol, ghrelin, and leptin are interacting with their sleep cycles, their stress levels, and even the timing of their last meal. This is why scientists are now shifting the conversation away from rigid fasting windows and toward metabolic flexibility. Metabolic flexibility is your body's ability to switch between burning glucose and burning fat. In a healthy system, this switch happens smoothly. After you eat, your body burns glucose. When you stop eating, your body transitions to burning stored fat. But modern lifestyles filled with constant snacking, late-night eating, and high sugar intake have disrupted this natural rhythm. For many people, the body never fully switches into fat-burning mode. Even during fasting, researchers started noticing that people who ate late at night had worse blood sugar control the next morning, even if they fasted for the same amount of time. That means the clock matters just as much as the fasting window. Your body follows circadian rhythms that control metabolism, hormone release, and cellular repair. When food enters the body late at night, it sends signals that conflict with these rhythms. This discovery gave rise to a new approach called early time-restricted eating. Instead of eating from noon to 8 p.m. like the traditional 16-8 model, studies began showing that eating earlier in the day may produce stronger metabolic benefits. In one controlled study, participants who ate between 8 a.m. and 4 p.m. improved insulin sensitivity, reduced hunger hormones, and stabilized blood sugar levels. Interestingly, they reported feeling less hungry in the evening, even though they stopped eating hours earlier than the typical fasting schedule. This challenges one of the biggest assumptions people had about fasting. For years, many believed that skipping breakfast was the key to fat loss. But newer research suggests that eating earlier in the day may actually align better with your body's natural metabolic peak. Your cells process glucose more efficiently in the morning and early afternoon. By nighttime, insulin sensitivity declines, meaning your body struggles more to manage carbohydrates and calories. Another major change in fasting science is how researchers now understand stress and fasting. Fasting was once viewed as a universal metabolic benefit, but scientists now know that fasting is also a stress signal. When you stop eating, your body activates stress pathways that trigger adrenaline, cortisol, and growth hormone. In moderate doses, this is beneficial. It increases fat breakdown and activates cellular repair systems like autophagy. But if the body is already under chronic stress, adding prolonged fasting can backfire. This is why some people experience fatigue, hormonal disruption, or sleep problems when they push fasting too aggressively. The body interprets extreme fasting as a survival situation. Instead of increasing metabolism, it may slow down metabolic processes to conserve energy. This phenomenon is sometimes called metabolic adaptation. The body becomes more efficient at using fewer calories, which can make fat loss harder over time. Researchers studying female metabolism have also discovered that hormonal cycles interact strongly with fasting patterns. Women's bodies are more sensitive to energy availability because of reproductive hormone regulation. Extended fasting during certain phases of the menstrual cycle may increase cortisol levels and disrupt hormonal balance. This doesn't mean women shouldn't fast, but it suggests that fasting strategies may need to be adjusted according to biological rhythms rather than applied as a rigid rule. Another breakthrough in fasting science involves something called the metabolic switch. This is the point when the body shifts from glucose burning to fat burning and ketone production. For years, people believed this switch happened automatically after about 12 hours of fasting. But newer research using metabolic tracking shows that the timing varies widely depending on a person's diet, insulin sensitivity, and physical activity levels. Someone who eats a high-carbohydrate diet may take much longer to enter fat-burning mode compared to someone who eats a lower-carbohydrate or metabolically balanced diet. This means two people doing the same fasting window could experience completely different metabolic outcomes. For some individuals, fat burning may start after 12 hours. For others, it may take 18 hours or longer. Scientists are also exploring how movement affects the fasting response. When people exercise during a fasted state, the body often accelerates the metabolic switch. Muscle activity depletes stored glycogen, encouraging the body to tap into fat stores more quickly. This is one reason why light activity like walking in the morning before breakfast has gained attention in metabolic research. But perhaps the most fascinating shift in fasting science involves the role of cellular repair. One of the main reasons fasting gained popularity was because of autophagy. Autophagy is the process where cells clean out damaged proteins and recycle components to maintain cellular health. It's like an internal repair system that helps reduce inflammation and may protect against aging-related diseases. For years, people assumed that longer fasting automatically meant more autophagy, but recent studies suggest the relationship is more nuanced. Autophagy depends not only on fasting duration but also on nutrient signaling pathways like mTOR and AMPK. These pathways respond to protein intake, energy availability, and exercise. This means that strategic fasting combined with proper nutrition may activate repair processes more effectively than simply extending fasting hours. Researchers are now investigating something called fasting mimicking patterns. Instead of strict daily fasting windows, these patterns use cycles of reduced calorie intake or specific nutrient combinations to trigger similar metabolic responses without prolonged deprivation. Early results suggest these approaches may help improve metabolic health while reducing the stress response associated with extreme fasting. Another surprising discovery involves the gut microbiome. The trillions of bacteria living in your digestive system follow daily rhythms just like your body does. When you eat late at night or continuously snack, these microbial cycles become disrupted. This can affect digestion, inflammation, and even weight regulation. Studies now show that consistent eating and fasting cycles help restore microbial balance. In experiments where participants maintained consistent meal timing each day, gut bacteria diversity improved and inflammatory markers decreased. This suggests fasting may work not only by changing hormone levels, but also by synchronizing the biological rhythms of the microbiome. Sleep has also emerged as a powerful factor influencing fasting outcomes. Poor sleep can increase insulin resistance and hunger hormones, making fasting feel much harder. When someone sleeps less than 6 hours regularly, ghrelin levels increase, which stimulates appetite, while leptin levels drop, reducing the feeling of fullness. This hormonal shift can sabotage fasting efforts even if the fasting window is followed perfectly. Scientists now emphasize that fasting cannot be separated from sleep quality. A person who sleeps well and aligns their eating with circadian rhythms may experience strong metabolic benefits with shorter fasting windows. Meanwhile, someone with poor sleep and irregular eating times may struggle even with longer fasting periods. Another major shift in fasting science involves the concept of metabolic individuality. For years, health advice treated everyone the same. But new research using continuous glucose monitors shows that people respond to food and fasting in dramatically different ways. Two individuals eating the exact same meal can experience completely different blood sugar spikes. This variability means that fasting strategies that work well for one person may not work the same way for another. Personalized approaches based on metabolic response, activity levels, and sleep patterns may be the future of fasting science. Interestingly, some researchers are even questioning whether daily fasting is necessary at all for certain metabolic benefits. Studies on alternate day fasting and periodic fasting suggest that occasional longer fasts combined with regular balanced eating may produce similar results to daily time-restricted eating. The body appears to respond strongly to metabolic change rather than constant patterns. When fasting becomes too predictable, the body may adapt and reduce its metabolic response. Introducing variation, sometimes shorter fasts, sometimes longer gaps between meals, may stimulate metabolic flexibility more effectively. One of the most misunderstood aspects of fasting is hunger. Many people assume hunger increases the longer you fast, but hunger actually follows hormonal waves. Ghrelin, the primary hunger hormone, rises and falls at times when the body expects food. If someone consistently eats at noon every day, ghrelin will spike around noon even during a fast. But if meal timing changes gradually, these hunger waves begin to shift. This is why people who practice fasting regularly often report that hunger becomes easier to manage after a few weeks. The body recalibrates its expectations. There is also growing interest in something called protein timing during fasting schedules. While fasting focuses on periods without food, the meals that break the fast play a crucial role in metabolic outcomes. Protein intake helps preserve muscle mass, which is essential for maintaining metabolic rate. When fasting is combined with inadequate protein, the body may break down muscle tissue, reducing long-term energy expenditure. Muscle is metabolically active tissue. The more muscle someone maintains, the more calories their body burns at rest. This means effective fasting strategies must consider not just the fasting window, but also the nutritional composition of meals. Hydration is another overlooked factor. During fasting, insulin levels drop, which causes the kidneys to release more sodium and water. This can lead to mild dehydration or electrolyte imbalance if fluids and minerals are not replenished. Symptoms like headaches, fatigue, or dizziness during fasting are sometimes caused by electrolyte shifts rather than lack of calories. Recent discussions in metabolic research emphasize balancing electrolytes such as sodium, potassium, and magnesium during fasting periods. Maintaining proper hydration supports energy levels and helps the body adapt to fasting more comfortably. The past 5 years have also brought attention to the psychological side of fasting. When fasting becomes rigid or extreme, it can create an unhealthy relationship with food. Researchers now encourage flexible fasting approaches that prioritize metabolic health without promoting restrictive behaviors. Fasting is increasingly viewed as a metabolic tool rather than a strict lifestyle rule. Just like exercise routines vary depending on goals and conditions, fasting strategies may need to adapt to individual health status, age, and daily stress levels. One of the most exciting developments in fasting research is the connection between fasting and brain health. During fasting, the body produces ketones, which are alternative fuel molecules derived from fat. Ketones are not just energy sources. They also act as signaling molecules that influence brain function. Studies show that ketones can increase the production of brain-derived neurotrophic factor, a protein that supports neuron growth and cognitive resilience. This may explain why some people experience mental clarity during fasting periods. However, the degree of this effect depends on how efficiently the body transitions into fat-burning mode. Scientists are now exploring whether intermittent fasting may help protect against neurodegenerative diseases by enhancing cellular repair and reducing inflammation in the brain. While research is ongoing, early findings suggest that metabolic flexibility plays a key role in cognitive health. Another emerging field involves the interaction between fasting and immune function. Short-term fasting appears to stimulate certain immune repair processes, including the regeneration of immune cells. However, prolonged fasting without adequate nutrition may weaken immune defenses. This again highlights the importance of balance. The goal is to create metabolic signals that activate repair mechanisms without pushing the body into excessive stress. When we step back and look at all these discoveries together, a clear message begins to emerge. Fasting is not simply about skipping meals. It's about restoring the natural rhythms that modern lifestyles have disrupted. For thousands of years, humans naturally experienced cycles of eating and fasting based on daylight, food availability, and activity patterns. Our bodies evolved to function within these cycles, but constant access to food, artificial lighting, and late-night eating have broken the rhythm. The new science of fasting is essentially about resynchronizing these biological clocks, eating earlier in the day, allowing periods without food, sleeping well, staying physically active, and maintaining balanced nutrition all work together to restore metabolic harmony. This is why many researchers now believe that the future of fasting will move away from rigid formulas like 16-8. Instead, it will focus on personalized metabolic timing, circadian alignment, and flexibility based on individual biology. In the coming years, wearable technology and metabolic tracking may allow people to monitor how their bodies respond to fasting in real time. Devices that track glucose, ketones, and sleep patterns could help individuals adjust their eating schedules for optimal health. What once seemed like a simple diet trend is evolving into a sophisticated field of metabolic science. And the biggest lesson from the past 5 years is that the human body is far more complex and adaptable than we once believed. The most effective fasting strategy may not be the longest fast or the strictest schedule. It may simply be the one that works in harmony with your body's natural rhythms, supporting energy, metabolism, and long-term health. For years, people believed that fat burning simply started after a certain number of fasting hours. The most common idea was that after 12 hours without food, the body would automatically switch from burning sugar to burning fat. This belief spread widely through books, fitness blogs, and social media posts. But modern metabolic research is revealing something far more complex. The moment when your body truly shifts into fat-burning mode is not controlled by the clock alone. Instead, scientists are discovering that the real trigger depends on something called the metabolic switching window. This window is influenced by your activity level, the composition of your last meal, and the amount of insulin circulating in your bloodstream. To understand this idea, imagine your body as a hybrid engine. It can run on two main fuels, glucose and fat. Glucose is the quick energy source that comes mostly from carbohydrates, while fat is the stored fuel that provides long-lasting energy. Throughout the day, your body constantly moves between these two fuels depending on what you eat and how active you are. When you eat a meal high in carbohydrates, your body prioritizes burning glucose. Insulin rises, glucose enters the bloodstream, and your cells absorb that energy for immediate use. At that moment, fat burning slows down because the body prefers to use the most available fuel first. The shift toward fat burning begins when glucose levels start dropping and insulin levels fall low enough to allow stored fat to be released from fat cells. This process is known as lipolysis, but the timing of this shift is not the same for everyone. Two people could stop eating at the exact same time, yet their bodies might enter fat-burning mode hours apart. Researchers studying metabolism began noticing this variability when they started using continuous glucose monitors and metabolic chambers. These tools allow scientists to see exactly which fuel the body is using at different times. What they found surprised many experts. Some people began burning fat around 10 hours after their last meal, while others remained mostly in glucose-burning mode even after 16 hours. The difference often comes down to the metabolic switching window. This is the period when the body gradually moves from relying mainly on glucose to relying more on stored fat. Instead of an instant flip of a switch, the process is more like a dimmer, slowly changing brightness. Hormones shift, glycogen stores decline, and the body gradually opens the pathway toward fat metabolism. One of the strongest factors affecting this window is the composition of the final meal before fasting. A meal high in refined carbohydrates can keep insulin elevated for many hours. Insulin helps cells absorb glucose, but it also signals fat cells to hold on to stored energy. As long as insulin stays elevated, fat release remains limited. This means someone who ends the day with sugary desserts, refined carbs, or sweet drinks may delay the metabolic switch much longer than someone who finishes with a balanced meal containing protein, fiber, and healthy fats. The balance of nutrients in that final meal can influence metabolism for hours afterward. Protein behaves differently from carbohydrates. It does not cause a sharp blood sugar spike, but it still triggers a moderate insulin response because insulin helps move amino acids into cells. Fat, on the other hand, causes very little insulin response. Meals that include healthy fats with protein and fiber often produce slower digestion and steadier blood sugar levels. This stability allows insulin to fall sooner, helping the body move toward fat burning more easily. Physical activity also has a powerful influence on the metabolic switching window. Movement requires energy, and when muscles contract, they begin using stored glycogen. Glycogen is the stored form of glucose kept in the liver and muscles. As glycogen levels decline, the body begins searching for other energy sources. This is when fat metabolism begins increasing. Researchers have found that even light activity like walking can speed up this transition if done during a fasting period. Movement lowers circulating glucose and encourages the release of fatty acids from fat cells. This is why many scientists now talk about fasted movement. A simple morning walk, light stretching, or gentle activity before breakfast may help open the metabolic switching window earlier in the day. The body senses that energy is needed and begins tapping into stored reserves. However, exercise intensity matters. Extremely intense workouts can raise stress hormones like cortisol and adrenaline. These hormones temporarily increase blood glucose to provide fast energy for the muscles. In some cases, this can briefly slow fat burning because the body switches back to using the newly released glucose. Moderate activity tends to create the most balanced metabolic response. It lowers glycogen stores without triggering excessive stress signals. Over time, regular activity trains the body to switch between fuels more efficiently. Insulin sensitivity is another major factor in determining how quickly the metabolic switch occurs. Insulin sensitivity refers to how effectively cells respond to insulin signals. When insulin sensitivity is high, cells absorb glucose efficiently, and insulin levels fall relatively quickly after meals. When insulin sensitivity is low, the body must produce more insulin to manage blood sugar. Insulin stays elevated longer, which keeps fat cells locked in storage mode. People with insulin resistance may therefore experience a delayed metabolic switching window even if they fast for many hours. Improving insulin sensitivity through movement, balanced nutrition, and good sleep can shorten this delay. Sleep itself plays a surprisingly important role in metabolic switching. During deep sleep, growth hormone is released and insulin sensitivity improves. These processes support fat metabolism and cellular repair. When sleep is poor, cortisol levels may rise while insulin sensitivity declines. This hormonal environment can keep blood sugar elevated longer and delay the shift toward fat burning. Circadian rhythms also influence this process. The body operates on a roughly 24-hour biological clock that regulates metabolism, hormones, and digestion. During daylight hours, metabolism is generally more active and insulin sensitivity higher. At night, the body prepares for rest and metabolic activity slows. Eating late at night can disrupt this rhythm. When food is consumed during a time when metabolism is naturally slowing down, glucose may remain elevated longer than usual. This keeps insulin higher into the night and delays fat metabolism. Researchers observing meal timing noticed that people who finished eating earlier in the evening often entered fat-burning mode sooner overnight compared with those who ate late dinners. The body simply had more time to process glucose before sleep. Liver glycogen storage also plays a role in the metabolic switching window. The liver stores glycogen and releases it into the bloodstream between meals to maintain stable blood sugar. When glycogen stores are full, the body relies on them before turning to fat. Fat burning begins increasing significantly once liver glycogen starts declining. The speed of this decline depends on activity levels and diet composition. Diets very high in carbohydrates refill glycogen stores quickly and may delay the switch toward fat metabolism. Over time, the body can become more efficient at this transition. This ability is known as metabolic flexibility. A metabolically flexible body can smoothly shift between glucose and fat, depending on energy needs. People with good metabolic flexibility often experience more stable energy levels and better blood sugar control. Training metabolic flexibility happens through repeated cycles of eating, fasting, and physical activity. Each time the body moves from glucose burning to fat burning, the pathways responsible for that shift become stronger. Inside the cells, enzymes that break down fatty acids become more active. Mitochondria increase their ability to process fat molecules and convert them into energy. As these systems improve, the body gains easier access to stored fat. Ketone production also increases as the metabolic switch progresses. Ketones are molecules produced when the liver breaks down fatty acids for energy. They can fuel many tissues, including the brain, and provide a stable energy source during fasting. Hydration and electrolytes support this metabolic process as well. During fasting, insulin drops and the kidneys release more water and sodium. Maintaining hydration and balanced electrolytes helps support circulation and energy transport as the body shifts between fuels. Hormones like glucagon, growth hormone, adrenaline, and noradrenaline also help regulate the metabolic switching window. As insulin declines, glucagon encourages fat breakdown and glucose release from the liver. Growth hormone helps preserve muscle tissue while supporting fat metabolism. Together, these signals create the gradual transition from glucose dependence to fat utilization. Rather than a single moment, the metabolic switch is a progressive shift where glucose usage decreases and fat metabolism steadily rises. Lifestyle habits strongly influence how wide or narrow this window becomes. Someone who eats late at night, sleeps poorly, experiences chronic stress, and remains physically inactive may experience a delayed metabolic switch. Their body may remain dependent on glucose even during long fasting periods. In contrast, someone who eats balanced meals earlier in the day, stays active, manages stress, and sleeps well may enter fat-burning mode much sooner. The metabolic switching window is therefore not fixed. It changes depending on daily habits. Small adjustments in meal composition, physical activity, sleep timing, and stress management can gradually shift the body toward more efficient energy use.